Hi everyone. So today we're going to be talking about a different type of limit from what we were talking about before. Before we get there, I just want to quickly point one thing out. So I've noticed that a lot of people haven't really started the online homework yet. That's your business. I can't really tell you how to do your work, but I just wanted to remind you that I really recommend that you work on the homework throughout the week, and not just from the sense that I'm telling you, oh, like don't procrastinate. It really is better for your learning, or at least there have been studies that show that people learn best when you practice the thing that you learned very close to when you actually learn it. So I just think it would really benefit you if you work on the homework throughout the week. And I also think it will just make it easier for you because rather than facing this kind of overwhelming list of questions, you'll be dealing with questions that just have to do with what you learned that day. So I just want to quickly remind you that if you go to the module for each week, if you go to the summary at the top, it tells you each day, which, oops, that's week one, but I guess that doesn't really matter. So week two, it tells you for each day what are the homework problems that you can do after watching each video. So that's how I'd recommend you do it. Just wanted to quickly remind you of that just in case it kind of slipped your mind. I know I talked about it in the introduction video, but it's been a while. Okay, so let's get back to the math. So in the book, we're now going to be in section 2.6. So this section is called Limits at Infinity. Okay, so we're just going to be spending one video on this. Typically, I'd probably spend a little bit longer, but like I said, I've been trying to make some choices about what to kind of cut short just because we have a week less than we normally would in a quarter. So I want to make sure that we get to the really important stuff. Okay, so far in this class, when we've been talking about limits, which is basically all we've been mostly doing, we have been dealing with limits of the form the limit as x approaches a number a of a function, where a is a real number, right? So like the limit as x approaches 0, or the limit as x approaches 5, or some real number. So in today's video, we're going to be talking about limits that instead are of this form. So today, we will deal with limits of the form the limit as x approaches negative infinity of f of x, and the limit as x approaches infinity of f of x. So in some ways, these types of limits are similar to what we were doing before, because if you think about it, like why do we use limits? So we saw that you can take a limit of like any function you want, basically. But usually, if you're taking a limit as x approaches a of a function, you're doing it because you can't just go ahead and plug in a, right? Oftentimes, you're taking a limit because you're trying to figure out, okay, the function is not defined at a, let me kind of get an idea of where the function is heading. And so similarly, you can't plug in infinity or negative infinity into a function, right? Infinity and negative infinity are not numbers. So you can never like plug infinity into a function. That just literally doesn't make sense. And so in a similar way, limits will allow us to kind of like get a sense of the trend of a graph because we can't just plug something in. At the same time, there's something that is just very fundamentally different about limits as we approach infinity. So I just want to kind of write down like intuitively what's going on here. So when you're doing a limit of the form as x approaches a of f of x, you're basically looking at what happens to the outputs as x is getting closer to a particular number a, right? So x is getting closer to 5, or x is getting closer to 0, something like that. So when you're doing functions or when you're doing limits that are limits as x approaches negative infinity or positive infinity, it doesn't really make sense to say x is getting closer to negative infinity because negative infinity is not a number. So really what's happening when we're dealing with these limits is we're looking at what happens as x gets, so if we're looking at negative infinity, we're thinking about what happens as x gets smaller and smaller. I think for a lot of us, when you hear the word small and you're thinking of a number, you think of like, oh, like zero point 0.5 is a small number or zero point 0.1. That's not what I mean here. When I say smaller, I mean like negative 1,000 or negative 1,000,000. So in today's video, if you hear me say, a very small number, what I mean by that is I mean like negative 1,000,000, something like that. If I say a number that's close to zero, that would be something like zero point 0.1 or zero point 0.5 or whatever. And so similarly, when we're looking at the limit as x approaches infinity, now we're looking at x gets larger and larger. So basically, another way of talking about these limits at infinity, as they're called, is what's called the end behavior of a function. So if you took Math 141 at North Seattle College, then you probably learned about this idea of end behavior, specifically in the context of polynomials. And so we'll get to some examples of that in a minute. So let me kind of write down what we were just saying. So the limit as x approaches negative infinity of a function and the limit as x approaches positive infinity of a function are descriptions, of the end behavior of f of x. So what do we mean by end behavior? We basically mean like the ends of the function. If you're looking like at the graph, you're looking at really far left and really far right on the graph. Where are those ends kind of pointing? Or you can think of just like the ends of like plugging in the very smallest and the very biggest numbers. So when you learned about end behavior in 141, you use this kind of notation where you said like as x goes to infinity, f of x goes to infinity or something like that. That was basically like sort of a warm up for limits. So you weren't using limit notation, but it was really the same idea. And if you don't know what I'm talking about with that, that's fine. But I just wanted to make that connection in case you did see end behavior in another class. Okay, so I want to just sketch a couple of quick examples, and then we'll get to some more like concrete examples. But just to kind of give you a little bit of intuition behind what is going on when we're talking about end behavior. So let's say, for example, you have a graph that looks like this. It's a weird arrow I drew. No, okay. So let's say you have a graph that looks like this. So if you were looking at this graph and this was a function f of x, this would be an example of a function where the limit as x approaches negative infinity of this function. So how would you go about figuring out what that is? Well, you're basically looking at, as you go left on the number line. So as you're kind of plugging in numbers that are further and further to the left. And actually, sorry, I said negative infinity, but for some reason I wrote down infinity. So this should have been negative infinity. So you're going out to the left and you're seeing where is the graph heading? Where are the y values heading? Because when we're evaluating limits, we're always looking at where the y values are heading. And so in this case, the y values are heading towards infinity, right? They're getting bigger and bigger and bigger. And so you would say the limit as x approaches negative infinity of f of x is equal to infinity. And then the limit as x approaches positive infinity of f of x would be equal to, so now we're looking at, maybe I'll color code this so that you have some reference here. So now we're looking at, like, as you plug in bigger and bigger values, where are the y values going? And in this case, it's getting smaller and smaller as you plug in bigger and bigger numbers. So the limit would be negative infinity. So that's kind of one type of situation that you might have when you're doing limits at infinity is one where you have the ends of the function are like either pointing up or pointing down, or one of them's pointing up, one of them's pointing down. You could also have a graph that looks more like this one. So you might have a graph where it kind of eventually flattens out to a particular height. So let's say that this height that it's flattening out to, in this case, let's just say it's 1. And so in this case, if you're doing the limit as x approaches negative infinity, you're seeing, where are the y values heading? And maybe let me just label this, let's call this function g of x. So looking at this graph, if you're talking about the limit as x approaches negative infinity, you're looking at what height are the y values approaching as you plug in smaller and smaller x values, and the answer is 1. Whereas if you're looking at what's happening as you plug in bigger and bigger x values in for x, so that would mean you're now going to the right and seeing what's going on in the graph. Well, in that case, it's also settling down to a height of 1. And so the second picture is what's called a horizontal asymptote. At in this case, it would be at a height of y is equal to 1. So a horizontal asymptote is when your graph kind of eventually flattens out to a particular height. Okay, so I want to look now at some more specific examples. So we're going to talk about, in this video, polynomials. Then we'll talk about a couple of other just kind of random functions that I wanted to discuss. And then the main thing that we'll be looking at in the video in terms of like kind of new stuff is rational functions. And we'll be learning a very specific method for evaluating limits dealing with rational functions. So maybe I'll go to a new page here. Okay, so the first thing we're going to be talking about is end behavior. And so when I say end behavior, that again, it's synonymous with saying the limits at infinity. It's really the same concept. It's just a different way of saying it. So this next thing is something that you should have learned in 141, so I don't want to spend too much time on it, but I just want to kind of refresh your memory. So basically, when you have a polynomial, if you look at what is the degree of that polynomial, so the degree means the highest exponent, and then what is the leading coefficient? So the leading coefficient basically means what is the coefficient of the highest power of x. So if you look at whether the degree is even or odd, and whether the leading coefficient is positive or negative, those two pieces of information together tell you what the general shape of the graph is going to look like. So I want to kind of divide polynomials. We're going to write down like kind of 4 different cases of what polynomials might look like. And again, I'm not going to really delve too deeply into why they look like this. I probably won't be able to help myself, and I'll start talking about why, but I don't want to spend too long on this part. Okay, so probably go off screen here, but I'll just scroll over when we get there. Okay, so first case is if you have an even degree and a positive leading coefficient, then you're going to end up with a graph that basically looks, the general shape will look like a parabola. I'm not saying that the graph will exactly be a parabola, but it will kind of look like one. So this is a case where, again, the degree is even and the leading coefficient, and I'm going to abbreviate here for the sake of space, leading coefficient is positive. So examples of functions like that, so just to give kind of the most simple example would be f of x is equal to x squared. But now just to kind of throw in a more complicated example, 2x to the 6th minus 5x cubed plus 7x plus 1 would also have a graph whose general shape would look like the one that's graphed here. And I'll pull the graph of this up in a second. So any function that has a even, or any polynomial that has an even degree and a positive leading coefficient is going to have a shape like this. And so what that means is that the limit as x approaches negative infinity of the function is going to be equal to infinity, because as you plug in smaller and smaller numbers, it's going to be giving you more and more positive results. And basically, just to quickly describe why it is that happens, well, in the case of x squared, I think it's easy to see it's because you're squaring it, right? It's going to become positive. And then in the case of other functions, so like if you're plugging in a really small negative number into g of x, let's say, you would get a positive number here, right? Because you would be raising that negative number to the 6th power, which would make it then positive. And then you would have some other stuff here, but because you're plugging in a number like negative a million or some very, very negative number, raising that number to the sixth power is going to give you a much bigger result than anything else. So basically, that's why you only have to look at the degree and the leading coefficient. It's because the sort of first part of your polynomial is really the part that dictates what's going to happen with the end behavior. It's, these other parts here are going to change what like the middle of the graph looks like, but when it comes to the end behavior, that's really has to do with just this leading coefficient and the degree. Okay, so on the same note, if you take the limit as x approaches infinity of your function, you're also going to get infinity. So let me just pull up this graph. So this is the graph of the second function I gave you as an example. So you can see it doesn't exactly look like a parabola, but it does have that same general shape. So it still has that same limit if you were to take, the limit as x approaches infinity and negative infinity of this. Okay, so next case is if and I drew all these. I do the same thing actually when I'm presenting this in class. I always draw these ahead of time, and then I realize that I didn't really do it how I wanted. So the next one is if you have still an even degree, but now you have a negative leading coefficient, that means the graph is going to have a general shape like kind of like an upside down parabola. And still didn't do this exactly what I want. Let me just fix that. Okay, so this is if you have a degree that is still even, but a leading coefficient that is negative. Well, then you're going to have, and maybe I'll just put these on the next line. So it happens when I try to organize myself ahead of time, it doesn't work. So if you have a leading or a degree that's even and a leading coefficient that's negative, that means that your graph is going to look kind of like negative x squared. Another example of a function that has that same end behavior would be negative 5x to the fourth plus 10x cubed plus 4, because it's really just that first term that controls what the whole graph looks like. So for this function, the limit as x approaches negative infinity of the function is always going to be equal to negative infinity, because it's going down on both ends. And the limit as x approaches positive infinity is also going to be negative infinity. So it goes down on both ends. Okay, so let's do the two other cases. So the other ways that polynomials could look is, so one possibility is it could point up on one end like this and down on the other like that. So this would be a case where the degree is odd and the leading coefficient is positive. So examples of that would be functions like, so simplest example would be f of x is equal to positive x cubed. And then any polynomial with the odd leading or odd degree and positive leading coefficient would work. Just to give an example that maybe isn't quite what you would think of, but that technically is true, would be something like 2x plus 5. So technically, linear functions are considered polynomials. And so the highest power in this polynomial is 1. So that's an odd number, right? 1 is an odd number. So that works. And if you think about it, what would that function look like? It's a line. So it would look like this. So it would have the same end behavior. So what is the limit in this case? Well, the limit as x approaches negative infinity of this function is going to be negative infinity because it points down on the left. And the limit as x approaches positive infinity of functions like this is going to be positive infinity because it goes up on the right. Okay, last one. So if you have a function that has still an odd degree, but now has a negative leading coefficient, so degree odd, leading coefficient negative, now it's going to look like this last one that I drew. So examples of this, most simple example would be f of x is equal to negative x cubed. But you could also have anything with, again, that negative leading coefficient and odd degree. So negative x to the fifth minus 2x to the fourth minus 3 would still have that same shape. And so therefore, the limit as x approaches negative infinity in this case is actually positive infinity, right? Because these types of functions go up on the left and down on the right. And again, like, why do they have the shape? I don't want to get too much into it in this video just for the sake of time, but if you just kind of think about it, like, think about what happens when you plug in a really big or a really small number. And you can even like test it out. One thing that like, so how, when we first learned about limits, we were just plugging in numbers. You can do a similar thing here. You can always plug in. So if you're taking the limit as x approaches infinity, you can plug in like 100 and 1,000 and 1,000,000 and use those numbers to kind of get a vibe of where the function's heading. And then for negative infinity, you would want to plug in like negative 100, negative 1,000, negative 1,000,000 to get a sense. But I do expect you to know these. So I do expect that you would know for a polynomial what the end behavior is, what the limit as x approaches negative and positive infinity, again, because it is kind of a review from pre-calc. So I want to look at two other examples where we're just going to kind of, again, do this by looking at the graph. And then we're going to get into some algebra methods that we're going to use for rational functions. So I'll just say a couple of other examples. So basically, one of the main kind of points of 141 and 142, pre-calculus 1 and 2 at North, was for you to get really familiar with a few different types of functions. So polynomials, rational functions, which we'll get to in a little bit, exponential functions, trig functions, all of those types of functions. I expect in this class that you have some basic familiarity with what the shapes of those graphs look like. So for example, let's say that you wanted to figure out what is the limit as x approaches infinity of sine of x. So I'd expect that you could, graph the basic shape of this and try to use that to figure out what's going on. So let's sketch the graph of sine of x. So we know that it's a periodic function, right? So it goes up and down like this. It does the same thing over here. So maybe pause the video, and I shouldn't put those arrows because that makes it look like, oh no. The arrow makes it seem like it's going to keep going up or keep going down, but we know that it kind of goes back and forth, right? Let's see if I can do that without, yes, okay. So maybe pause the video, and I want you to think for a minute about what do you think the limit is for this? Maybe compare it to some of the other examples we did and then see what you think the answer would be. So in this case, the limit actually does not exist. And so why does it not exist? Well, basically, when you're looking at a limit as x approaches infinity or negative infinity, you're looking for a general trend. So we saw some examples here where it's like, oh, the graph is either pointing up or it's pointing down, it's heading this way, it's heading that way. We also saw an example on the previous page where the graph was like eventually flattening out to a horizontal asymptote, and so that would have a limit of 1. But sine of x doesn't do either of those things. It does not keep getting bigger and bigger and bigger. It does not flatten out. It just kind of keeps doing its same thing over and over. So the limit doesn't exist basically because the function keeps going back and forth between different values. It never kind of settles out on one value, and it never has a general trend of getting bigger or smaller. So maybe let me try to write that in words. So because as x gets larger and larger, so I'll use x right arrow infinity as an abbreviation for that, f of x equals sine of x goes back and forth, repeating infinitely, right? It keeps it, if you like pull up the graph of sine of x on Desmos and scroll right, it's going to keep doing that same thing forever. It does not eventually grow larger and larger, so that would be if the limit equaled infinity, but it also doesn't eventually grow smaller and smaller. That would be if the limit equaled negative infinity. And then it does not flatten out to a particular y value either. So the limit does not exist. So one more example I want to look at before we get into looking at rational functions. So let's try to find the limit as x approaches negative infinity and positive infinity. We're going to do both of e to the x. So again, this is an example of a function that I would expect that you know how to sketch the general shape of this function. So what does e to the x look like? Basically, as you plug in bigger and bigger x values, it goes up and up and up, right? It's an exponential function. And then it has a y-intercept of 1, right? Because e to the 0 is equal to 1. So it kind of goes like this up to the right. And then on the left, as you plug in negative numbers, you're going to get smaller and smaller values like this. So one thing to note is that on the left side, it never actually goes below the x-axis, right? Because let's say you plug in like negative 100, that's e to the negative 100, which is 1 over e to the 100. So you get these really small fractions, but you never get a negative number. And so based on what we can see going on in this graph, we can see, and I guess I should have, here, let me move this. Maybe I'll just write it here in another color actually. So the limit as x approaches negative infinity of this function is equal to 0, right? Because as we go to the left, as we're plugging in smaller and smaller numbers, the graph eventually flattens out to a height of 0. Whereas if we are approaching positive infinity, well, then we're plugging in bigger and bigger numbers for x, so we're going this way. And as you plug in bigger and bigger numbers for x, the y values also get bigger and bigger. And so the limit as x approaches infinity of e to the x is equal to infinity. So that's just kind of a grab bag of different types of functions that you might be dealing with. So now we're going to get into rational functions. So as I warned you, this video is definitely going to be a little bit longer than some of the other ones. So if you kind of need a break, this might be a good pausing point. I will say that the stuff that we've talked about so far, we are going to use some of it. So we're going to definitely be using these polynomial stuff in the next part. But your homework is not going to directly test you on any of the stuff that's written on this page. The homework is really going to be more about rational functions. So that's what we're going to look at now. Okay, so we're now going to be looking at end behavior or limits at infinity of rational functions. Okay, so rational functions, first of all, just to kind of remind you, those are functions where you have a polynomial over a polynomial. So just to kind of write down, that got really crooked. I'm trying so hard not to make my handwriting tilt up, but I just can't help myself. I'm just going to fix that one. So rational functions, just to remind you, those look something like, so we'll get to this example in a little bit, but one example would be something like 3x squared minus 5x plus 1 over x cubed plus 2. So that's an example of a rational function. So you may remember some stuff from pre-calculus where you learned about horizontal asymptotes and how to tell whether a rational function has horizontal asymptotes or not and where those horizontal asymptotes are. I'm not really going to be going over those rules because the way that we're going to be doing these limits, you don't need to know those rules. You are just going to be using this algebraic method that will always get you to the right answer as long as you kind of use it correctly. So there's one important fact I want to write down that is going to be something that we're going to be using a lot during these limits. So if you take the limit as x approaches either positive or negative infinity, so I'm just writing plus or minus to kind of write both of them in one, of a number divided by x to a positive exponent. So that limit is always going to be 0. And let me just write down what c and n represent, and then we'll come back to talking about why this is. So this is for any constant c. So c could be a negative number. It could be, maybe let me just say any real number, c. So c could be positive, negative, fraction, decimal, whatever, any real number c. And then, but in this example, n has to be a positive integer. So like 1 or 2 or 3 or 5 or whatever. So why is this limit 0? Well, think about what happens when you plug in really big numbers. So let's look at an actual kind of example of this. So let's say that you were trying to take the limit as x approaches infinity of 500 divided by x squared. So if you're plugging in bigger and bigger and bigger numbers for x, you're going to get things like, so the numerator is pretty big, right? 500. But let's say you plug in 1,000 for x. You're going to have 500 over 1,000 squared. So 1,000 squared has 6 zeros. It's going to be 1 million. If you plug in 10,000, then you'll have 10,000 squared in the denominator. That's going to have 8 zeros. So the bigger and bigger the number that you plug in for x, even though this numerator is kind of big, it's not really going to be big compared to the denominator. So you're going to end up with these really tiny fractions that are getting closer and closer to 0. And so that's why the limit of things that look like that is equal to 0. So basically what we're about to do, and I'll write this down in words too, is we will basically learn an algebra method that breaks down limits of rational functions into pieces of the form. I feel like I always misspell pieces. I'm just going to leave it. Hopefully that's right. Pieces of the form c over x to the n. So we're going to kind of use the fact we're going to always be coming back to this idea that we know that these limits are 0. And so if we can take other limits and break them into those pieces, we'll be able to see what parts are equal to 0 and what parts are left over and use that to find our final answer. So I want to, we're actually going to do the example that I first wrote up here. We're going to do the limit as x approaches infinity, or actually we'll do negative infinity to start, of this function at the top. And so I think the way I want to organize this, and maybe I'll just go to a new page to, did I already use this page? Yeah. I'll just go down here actually. So I'm going to, on one side, write down kind of the general method, and then on the other side, we'll do it for the function. So the first thing that we're going to do in general, so I'm just going to be writing down this kind of general method. The first step that we're going to do is we're going to identify the highest power of x that appears specifically not in the entire function, but specifically in the denominator. So in most cases, the highest power, or not in most cases, but sometimes the highest power will be in the denominator anyway, but if it's not, you need to only look at the highest one in the denominator. And we'll see an exception like that in a little bit. Okay, so I'm trying to decide what color to use. I'll use this magenta. So let's say that we're working on the limit, actually I changed my mind, I'll use purple. The limit as x approaches negative infinity of 3x squared minus 5x plus 1 divided by x cubed plus 2. So in this case, the highest power of x that appears in the denominator is this, it's x cubed. So what we're going to do next is we're going to um, take that highest power and we're going to divide everything in our both the numerator and the denominator by that fraction. So we're going to divide every term, both in the numerator and denominator, by, I'm just going to say by x to the n. And when I say x to the n, I'm referring to whatever the highest power was. So why are you allowed to do that? Well, basically, dividing by everything by x to the n is the same as multiplying the numerator and the denominator both by 1 over x to the n. So I'll write that out. So basically, we have the limit as x approaches negative infinity of 3x squared minus 5x plus 1 over x cubed plus 2. So you don't have to write this step out, but I'm just going to write it down to kind of emphasize what's going on here. What we're doing is we're taking both the numerator and denominator and we're multiplying both of them by 1 over x cubed. And you're allowed to do that, right? Anytime you have a fraction, you're allowed to multiply by the same thing in the numerator and the denominator. And so what's going to end up happening is that we're going to be left with negative infinity. Sorry, I dropped that negative sign. So I'll have 3x squared over x cubed minus 5x over x cubed plus 1 over x cubed divided by x cubed over x cubed plus 2 over x cubed. Cool. So the next step is to then go in and simplify everything. So 3 is going to be simplify each term. So we're going to have the limit as x approaches negative infinity. So 3x squared over x cubed is going to simplify to just being 3 over x. And then 5x over x cubed is going to simplify to 5 over x squared. And then 1 over x cubed cannot be simplified, so we'll just leave that as it is. And then in the bottom, we have x cubed over x cubed, so that's 1. And then we have 2 over x cubed cannot be simplified. Okay, so basically what have we done? We've taken our limit and just as promised, we've broken it into these pieces of the form c over x to the n. So why is that useful? Well, remember that when I gave you that list of kind of function rules, one of the rules was that if you're taking the limit of like a sum of different functions or a division of different functions or anything like that, you can take the limit of each part separately. So what we're going to do now is we're going to take the limit of each of these pieces individually and kind of put them all together and see what we're left with. So now we're going to take the limit of each term. And basically what we're doing, and I'm not going to write it out because it just like looks really crazy and takes a lot of time to write this out, but really what we're doing is we're kind of like bringing the limit inside and we're doing the limit as x approaches negative infinity of this. And then we're doing the limit as x approaches negative infinity of this. And then we're doing the limit as x approaches negative infinity of this, etc. So if you wanted to, you could write that out and write a limit next to all of them, but we're just going to kind of jump straight to the next step and actually write down what those limits are. So we're going to take the limit of each term, remembering that anytime we encounter one of those things that's of the term of the form c over x to the n, that limit is going to be equal to 0. So what are we left with? So like basically all of these things are going to equal 0, 0, 0, 0, 0. So what we're left with is 0 minus 0 plus 0 over 1 plus 0. And what is that equal to? That's equal to 0 over 1, which is just equal to 0. So that tells us that the limit as x approaches negative infinity of this function is equal to 0. So you might not be surprised by this result if you remember stuff from pre-calculus, you might remember that that if the degree of the numerator is less than the degree of the denominator, that you'll have a horizontal asymptote at 0. And that's great if you remember that. And I think intuitively, hopefully you can kind of understand why that is. It's because the denominator is going to get bigger way faster than the numerator. And so you're going to get these really tiny fractions that are close to 0. That being said, I do want you to know how to use this algebra method. So kind of like with some of the other limit stuff we've talked about, there's always kind of multiple ways to get to your answer, but I do want to make sure that you know how to use this algebra trick. So I'll try to be really clear on quizzes and tests and stuff of kind of telling you that and making sure you're aware of that. Let's look at the graph real quick. I think I did pull it up here. So is this it? I think so. Yes. So we can see that this function eventually, so we did the limit as x approaches negative infinity, and we can see that basically the y values get closer and closer to 0. And actually, we would have gotten the same answer if we did the limit as x approaches positive infinity for this specific function. For other functions, it will actually be different in the two directions. Okay, so we're going to do 2 more examples of using this method, and then that will be it for the video. So I appreciate your sticking with me. Okay, so the next example we're going to do is going to be the limit as x approaches, where did I write it down? Right here. Or no, not right there. Here we go. The limit as x approaches positive infinity of 3x squared plus 1 divided by 2x squared plus x minus 10. So you might remember from pre-calculus that if the degree is the same in the numerator and denominator, then what's going to happen is it's kind of if you think of this as like a battle between the numerator and denominator, it's a tie, right? If they're both the same degree. And so what these kind of functions end up having is a horizontal asymptote where the horizontal asymptote occurs at this fraction between the top 2 or the leading 2 coefficients. However, you don't need to know that because the method we're going to use is going to get you to that answer regardless. Okay, so first step is identifying that highest power of x. So in this case, it's x squared. So we're going to go through and we're going to divide everything by x squared. So we have 3x squared over x squared plus 1 over x squared. And by the way, so we'll see that this example is going to go pretty similar to the last one, but I would recommend sticking with me for the last example, the third one, because that one is actually going to bring up some slightly different stuff. So, so stay tuned for that. Okay, so if we now simplify everything, so if we go through and simplify each of these fractions, we'll have the limit as x approaches infinity of just 3. Right, the x squared cancel out. Then we have 1 over x squared. And then we have 2x squared over x squared, that's just 2. Then we have 1 over x. And then we have negative 10 over x squared. So again, we've kind of broken this down into its pieces, and now we can see which parts actually go to 0. So anything that is of the form, again, c over x to a power is going to go to 0. And so in this case, this is going to go to 0, this is going to go to 0, and this is going to go to 0. Because if you plug in a really big number for x, they're going to be these tiny fractions. So the limit as x approaches infinity is going to be 0 for those things. So if we go and we do those limits, we're going to get, so maybe just to say this, because I guess I didn't really say this in the last example. So if you're taking the limit of each piece here, so let's say now you're taking the limit of 3. So the limit as x approaches infinity of 3. What is that equal to? So that's just equal to 3, right? Because 3 is just a horizontal line at a height of 3. And so it's always going to be 3. It doesn't matter what x is. So sure, when x is really, really big, it's going to be 3. So when you're doing these limits, when you get to a number that's just already a number on its own, there's basically it's not going to be changed by plugging in any value for x. And so the limit as x approaches infinity or negative infinity or really anything is always going to be that number. So we're just left with 3 for that. And then we have 0. And then in the denominator, we have 2 for the same reason, and then we have 0, and then we have 0. So we're left with 3 over 2. So let's check out that graph just to confirm that we see that happening in the graph. So this one has, and I put it in here so you could really see. So the blue line is a dotted line, or the blue dotted line is a horizontal line at a height of 3/2. And so you can see that when you plug in really, really small numbers, the graph gets closer and closer to that line. And then same thing when you plug in really, really big numbers. So we can see that the graph does in fact get closer and closer to a height of 3/2 as you plug in, I guess we're doing the limit at positive infinity, so that would be out to the right. Okay, one more example. And like I said, this is going to bring up something a little different. So this is actually going to take us back to some of the stuff we were talking about at the beginning about polynomials and what their end behavior is. So let's now do one. So this is going to be one where now the degree of the numerator is going to be bigger than the degree of the denominator. So we're going to do the limit as x approaches negative infinity of 5x squared minus 3x plus 1, all divided by x minus 1. So this is an example where you have to be careful and make sure that you're dividing by the highest power of x that is in the denominator. So we're not going to divide everything by x squared. If you divide everything by x squared, you'll basically kind of get stuck. So instead, we're going to go through and divide everything by x. That's our highest power in the denominator. So we're going to go through, and we have 5x squared over x. We have 3x over x. We have 1 over x. Now we have x over x. Oops. It's not x. X over x. And we have 1 over x. So let's simplify everything. So if we simplify all of that stuff, we get, so 5x squared over x, that's just going to be 5x. 3x over x is 3, so minus 3. And then 1 over x cannot be simplified. And then the denominator, we have 1 minus 1 over x. So in this step, I want you to be really careful. What I see a lot of students kind of do something here that doesn't really make sense. We're not going to plug in infinity for x. You're never, ever, ever plugging in infinity. You can't plug in infinity. It's a number. Or sorry, it's not a number. So you cannot plug in infinity. What you can do is take the limit of these parts kind of separately. And so what we're going to do is we're going to kind of do this in steps. So we're going to leave this part kind of by itself. We're not going to take the limit of that part. And we're just going to take the limits of the 1 over x part. So these ones are both going to go to 0. And then we're just going to evaluate the limit of what's left once we're done with that. So we'll have the limit as x approaches negative infinity. And you're allowed to do this because basically I'm not writing out all the steps because it would look like a lot to write this down. But basically what are we doing? We're going in and we're kind of taking the limit of each part individually. And so if we can take the limit of each part individually, that means I can also kind of decide to take the limits of the parts that are circled while kind of waiting to take the limit of the other part. So now we're left with the limit as x approaches negative infinity of 5x minus 3 plus 0 over 1 minus 0. And so that's the same as the limit as x approaches negative infinity of 5x minus 3. So how do we answer this? Well, now go back to your kind of knowledge of what the general shapes of different functions look like. So what does this function look like? Well, it's a line. It's a line with a positive slope and a negative y-intercept, so it's going to look like this. And so that tells us that as x approaches negative infinity, so as you plug in smaller and smaller x values, the graph is going down. And so that tells us that the limit as x approaches negative infinity of this function is equal to negative infinity. So in this case, we would have gotten a different answer if we were instead doing the limit as x approaches positive infinity, we would get a different answer, right? Because the parts that go to zero would still go to zero. Like most of the method would be the same, but at the very end, when we go to kind of analyze our what we're left over with, instead the answer would be positive infinity. So you do have to be careful on these. You can't assume that you're going to get positive or negative infinity. Of course, there are ways to kind of figure it out by just like looking at what numbers you have. But the way I would like you to do it is to, again, use this method of dividing stuff through. And the point of this is that you start with something that's kind of more complicated and you end up with a function that's a lot easier to analyze. I think it's a lot easier to analyze what's going on um, with 5x minus 3 than it is with the whole function that we started with. So be careful with these again, and I put on the worksheet a couple of examples that are like this that kind of play out differently. So I definitely recommend doing those because I think they're a little bit trickier than this example we did together. So let me just last thing to show you this graph, just so we can see what that one looks like. So this is kind of a funny function because it has two pieces and they're kind of far apart. So we have a piece up here and then we have a piece down here. But what we can see is that the part that's to the left is getting smaller and smaller. The y values are getting smaller and smaller as x gets smaller and smaller. And one thing that's kind of interesting is that actually, let me actually not, there's something else I wanted to mention, but I think let's just stop it there. I feel like if I try to get into that, it'll take too long. So I think we're good on this. So like I said, I know this was probably kind of a long video and a lot of information, but we're not, like, it's important that we talk about these types of limits, but they're not going to keep coming up in the class in the same way that other limits will. So the other limit stuff we were doing at the beginning of the week, especially those different algebra methods, that is going to come up. In the future, this stuff isn't going to come up so much. So it's important that you see it once, but that's why I'm not really spending quite as much time on it. All right, so thank you all, and I will see you in the next video.